Welcome to the second part of our linear regression microlectures, advanced concept in linear regression, assumptions, dummy variables, and interaction. In this microlecture, we will build on what we covered in the previous presentation and focus on key aspects of model validity, how to work with categorical variables using dummy coding, and how to incorporate interaction terms to capture more complex relationships in data. In multivariate regression, residuals, defined as the difference between observed and predicted values, play a crucial role in assuming model validity. For the model to produce reliable results, these residuals must satisfy several key assumptions. They should exhibit constant variance, remain independent of each other, and follow a normal distribution. In multivariate linear regressions model, the predict value y is determined by the equation displayed on the slide. This equation defines a plane in a three-dimensional space, where each point represents a combination of predictor values. The actual observed value yi may not lie on this plane. The vertical distance between the observed point and the predicted value on the plane is called residual, EI. The goal of the model is to minimize the sum of these squared residuals, ensuring the best possible fit to the data. For a multivariate regression model to be valid, several conditions must be met. The relationships between predictors and the dependent variable should be linear, and predictors must not be perfectly correlated with each other. In time series data, residuals should not be autocorrelated. The model should not be overly influenced by outliers or extreme values, and it must be correctly specified, meaning it includes all relevant predictors while omitting those that are unnecessary. Finally, the predictors should be exogenous, which means that they must not be correlated with the error term. Further assumptions clarify how the regression models behave. The model assumes that the effect of independent variable on the dependent variable are both linear and additive. This means that unless explicitly added, interaction or nonlinear terms are not considered. It also assumes that predictors are measured without error, since measurement inaccuracy can lead to biased estimates. Additionally, in the context of ordinary least square regression, the values of the independent variables are considered fixed across repeated samples. A correctly specified model includes all relevant predictors and excludes irrelevant ones. Omitting an important variable can lead to biased estimates, while including unnecessary ones can distort the model. Classical regression also assumes that predictors are non-stochastic, meaning they are fixed and not random, although the normality of error is not required for estimating coefficients. It is essential when performing hypothesis testing or constructing confidence intervals. To ensure the validity of multivariate regression, we must verify that the key assumptions are met. Here is a summary of the assumptions and the recommended statistical test or diagnosis used to evaluate which one. Validating this assumption is essential for making reliable predictors and driving sound conclusions for regression models. To test whether an individual predictor significantly contributes to the model, we use the t-test. This involves checking if the predictor's coefficient is significantly different from 0. If the result is statistically significant, we conclude that the predictor does affect the independent variable. Confidence interval can also be used to evaluate a likely range in which the true coefficient lies. To assess the overall significance of the regression model, we apply the f-test. This test checks whether all the predictors taken together contribute meaningfully to explaining the dependent variable. A high F statistic suggests that the model provides a better fit than one with no predictors, meaning at least one independent variable has a significant level effect. Dummy variables are used to incorporate categorical variables with two levels into regression models. They are coded as 0 or 1 and allow us to compare groups such as male and female, or region A versus region B. In multivariate models, dummy variables helps isolate the effect of these categories while controlling for other predictors. Their coefficients indicate how much the outcomes differs between the included category by the reference group. Dummy variables are written in binary form, such as 0 for no and 1 for yes. One category is always excluded as the reference group. If a dummy variable is significant, it shifts the intercept of the model. For variables with more than two categories, we create one dummy for each level except the reference. For example, we can separately code categories like student, working, or pensioner. Coefficients are interpreted in relation to the reference group. It is important to avoid the dummy variable trap, which happens when all categories are included and perfect multicollinearity occurs. This example demonstrates how a dummy variable for a presence of a fireplace affects the model. When the fireplace is present, a dummy variable takes value 1. We change the intercept of the regression line. The slope remains the same, meaning the fireplace shifts the price level but not effect of other variables. If the coefficient of this dummy is specifically significant, it suggests that having a fireplace has a measurable impact on apartment price. Sometimes the impact of one independent variable on the dependent variable varies depending on the another. To model this, we include an interaction term which is the product of the two variables. Without the interaction, the effect of one predictor is constant. With the interaction term included, the effect becomes dependent on the value of the second variable. This allows us to capture interactions that better reflect real-world relationships. In this model, an interaction term is introduced between a continuous variable and a fireplace dummy. This changes not only the intercept but also the slope. When the fireplace is present, the effect of the continuous predictor becomes stronger. This indicates that the influence of one variable on the outcome depends on the category represented by dummy, relieving a more complex conditional relationship. We have reviewed a fundamental assumption underlying multivariate regression, learned how to incorporate dummy variables into regression models, and explore how interaction effect can provide deeper insight into the relationships among variables. I hope this microlecture will help you better understand how to apply linear regression techniques to more complex and realistic data scenarios. Keep practicing and you will be well on your way to mastering regression modeling. Thank you for your attention.